Welcome back. We were discussing Wald's equality and we were doing this example about stop when you are ahead, right. We have xi's are +1 or -1 with probability p and 1 minus p respectively, and you stop j is equal to min n for which, sorry, I should write it like this, min of n such that S n is equal to +1, right. The first time you hit +1 you stop, right, and we said theta is equal to probability that you stop eventually, and we said theta satisfies, we wrote out a quadratic equation, right. We said theta is equal to 1 if p is greater than or equal to half, and theta is equal to p over 1 minus p if p is less than half, right. This is where we were yesterday. So, if your probability of winning is at least half, then you are guaranteed to stop with probability 1. If your probability of winning is less than half, the probability that you eventually stop is only p over 1 minus p, which is less than 1, right, for p less than half. Therefore, in this case for p less than half, j is a defective stopping rule, because it can be infinite with positive probability. And similarly, you can calculate expectation of j. Okay, you can write a recursive equation similar to theta as follows. You can write expectation of j is equal to, so j is equal to 1 with probability p, right, because if you get +1 straight away you stop at j equal to 1, right. So, it is p times 1 plus, if you go down, right. So, you have gone down to -1, then what is the expected time to get to from -1 to +1? It is the expected time to go from -1 to 0 plus the expected time to go from 0 to 1, but these are both equal to expected j, right. Similar sort of an argument is theta. So, you have 1 minus p, you go down once, right, there is already one step that you are taking, plus expectation of j plus expectation of j, right, correct. So, this is for going from -1 to 0, this is for going from 0 to +1, all right. So, from this you can get expected j is equal to 1 over 2 p minus 1, this is for if p is less than half, of course expect j is infinite with probability, positive probability, therefore expected j will of course be infinite, right, but if p is greater than or equal to half, you get this expression, okay. So, this is so bottom line is that expected j is finite for p greater than half and expected j is infinite for p equals half. So, the case p equal to half is particularly interesting. So, it is a symmetric up and down walk, right, +1 -1. So, here you are guaranteed to eventually hit +1, right, with probability 1 you will stop, but the expected time for stopping is infinite. So, in this case Wald fails, right, in this case Wald holds, right, Wald equality holds, all right. Why? Wald's equality demands that, yeah, expectation be finite, expectation of j be finite. In fact, you can check, right, what is Sj? If you look at it, Sj is always +1, right. So, expected Sj is what, 1. So, the question is Wald says expected Sj is equal to x bar times expected j. If this were infinite, so if p equal to half, expected j would be infinite, right, x bar would be 0, expected s j is of course 1, right. Right, what is x bar? 2p minus 1, 2p minus 1, correct, all right. So, this guy is equal to 1 over 2p minus 1 as we calculated. So, it works, right. So, holds for p greater than half, right. P equal to half, you will have a problem, you will have 1 is equal to 0 times infinity, which is an absurd statement, right. So, expectation of j equal to infinity. So, even if j is a legitimate stopping rule, if your expected j is infinite, you cannot apply Wald, okay. Expected j is finite, you can apply Wald. So, shall we go ahead and prove Wald's equality? Wald's. See, the proof has a couple of subtleties, okay. So, I will point out what happens. There are a couple of points where you have to be very careful. You first write this Sj is equal to sum I equals 1 through infinity xi, sorry, maybe I should write n is equal to 1 to infinity xn indicator, because so you are basically j is the stopping time, right. So, you are summing all those xi's which are less than or equal to the stopping time, right, which is what Sj is. Now, you want to calculate expectation of Sj, correct, which is nothing but expectation of So, I have just taken what Sj is, I have taken expectation on both sides, right. Now, comes the first subtle point where I want to take the expectation inside the sum, okay. But the issue is that this is what kind of a sum? Infinite sum. So, you cannot always take a expectation inside an infinite sum. So, you can do it if the summands are non-negative, right, by monotone convergence theorem, right, but that may not be here, summands may not be non-negative, right, xn's could be negative like in the previous example, all right. So, you can't just take it in, right. So, I will eventually show that this works, okay. I will write n equals 1 to infinity expected xn, okay. This is justified. So, let me call this star, justified when expected j is finite, okay. I will justify this later, okay. Just take it for now, we will get back to this and prove that the star is justified, okay. So, next claim is that xn is independent of indicator j greater than or equal to n for all n, okay. This is why is this true? Basically, it is the stopping rule condition. You take the event j less than n, which is simply union I is equal to 1 to n minus 1, j is equal to I, right, correct. So, j less than n is the event that I stop before n, correct, strictly before n, which is the event that I stop at 1 or stop at 2 or stop at n minus 1, all right. Now, the event each of these j equal to I, the event that I stop at I, let us say stop at j equal to 2 or j equal to n minus 1 is independent of x n. Why? Stopping rule, right. So, each of this is independent of, so this event is x n, right, since j is a stopping rule. Correct. So, the event that I stop strictly before n can have only to do with x 1 through x n minus 1 and it has to be independent of x n. Now, so this is the slightly mind bending sort of a thing. So, you agree that the event j less than n is independent of x n, I think that is intuitive, but what is the complement of the event j less than n? J greater than or equal to n. So, if an event a is independent of, a complement is also independent of x n, right, this we know from basic probability. So, this implies j greater than or equal to n, which is simply the complement of j less than n is independent of x n. This is true for all n greater than or equal to 1. Okay. So, this makes sense, right, except that if you think about it, so this is a little bit of a confusing thing. See, j greater than or equal to n, right, is basically what? J is equal to n or j is equal to n plus 1 or j is equal to n plus I in general, right. See, the event j is equal to n is certainly not independent of x n, correct. In fact, j is equal to n is has a lot to do with x n, usually whether you stop at n or not will depend a lot on x n, right. Similarly, the event j is equal to n plus 1 or n plus 2 does depend on x n. So, then how is it that j greater than or equal to n is independent of x n, right. See, j greater than or equal to n means j is equal to n or j is equal to n plus 1 or j equals to n plus 2 and so on, right. So, none of these events are independent of x n, but it turns out that j greater than or equal to n is independent of x n. Okay. So, this is actually correct, there is nothing crazy going on here. Okay. So, the event j is equal to n or j is equal to n plus 1, so where you stop n or beyond depends on x n, okay, but whether j is greater than or equal to n is independent of x n. Okay. So, that is it is much easier when you go through j less than n and then take complements, then it makes perfect sense, but if you try to argue directly you seem to think you can't easily argue it, right, clear. So, but what I have written is clear, right, the event of stopping strictly before n is independent of x n. So, j less than n is independent of x n, therefore, j greater than or equal to is independent of x n. Okay. Okay, so that is great, right. So, then what can I do here? So, the event j greater than or equal to n is independent of x n. So, the indicator j greater than or equal to n is an independent random variable from x n, right, and if you have independent random variables are always uncorrelated. So, expectation of x y can be written as expectation of x times expectation of y. So, this just becomes, so this is because of the claim, right, n equals 1 to infinity expectation of x n times expectation of indicator j greater than or equal to n. Yeah. Now, what is the expectation of x n? Is equal to x bar, it is the common x bar, right, that comes out, n is equal to 1 to infinity. What is the expectation of indicator j greater than or equal to n? Indicator is a expectation of indicator is probability. So, that is probability that j greater than or equal to n, and what is this? This is like the this is the integral of the CCDF for this non negative random variable. So, this just becomes integer valued random variable, right. So, this is just expectation of j. Okay. So, you are done, except that. So, what is the only thing that you have not proven here? The star, the justification for taking the limit inside. Okay. So, if these things do not cause you sleeplessness, you can just take it as as true. Okay. But if it does make you sleepless, we will justify it. Okay. Ideally, it should make you sleepless, right. So, we have proved Wald's equality except for this justification for the step star above, which basically involves pushing an expectation inside an infinite summation. Now, pushing an expectation inside an infinite summation is not always justified. We need to impose some technical conditions under which this holds, and we have to basically prove that under the assumptions of Wald's equality, the pushing in of the expectation inside the infinite sum is justified. Okay. So, let us do that. So, the basic question which we are looking at is the following. When can we push an expectation inside an infinite summation? Of course, for a finite summation you can always push the expectation in, because the expectation is linear, right. Expectation of x plus y is always expectation of x plus expectation of y, and this is true even for a sum of n random variables. But you cannot always push an expectation inside an infinite sum, alright. So, essentially if you have, the question we are asking is this: when is it justified to say that, let us say yi's are some random variables, when can I say that the expectation of the sum is equal to sum of the expectation? I is equal to 1 to infinity expectation of yi. When is this justified? So, this holds, this is not always true, but it holds under two prominent sufficient conditions. Okay. The first sufficient condition is that if yi's are non-negative for each I, then you can push the expectation inside the infinite sum. The other sufficient condition is if sum over I equals 1 to infinity expectation of absolute yi, if this is finite, then we can still say that you can push the expectation inside the infinite sum. So, this holds under this or this, okay, you do not need both. Okay. If either one holds or two holds, then you can push the expectation inside the infinite sum. The condition 1 is a consequence of the monotone convergence theorem, and the sufficient condition 2 is a consequence of the dominated convergence theorem. All right. You can try and prove this as an exercise. I have given you the hint on what major result you have to use. All right. So, we are going to do, what we are going to do is we are going to use this sufficient condition to justify the pushing in of the expectation in the equation star here. All right. So, let us justify this equation star. Before that, so let me remind you of the Wald's assumptions. So, the Wald's assumptions are that J is a stopping rule for xi's, right, xi I greater than or equal to 1. We have assumed also that expectation of J is finite, and we have assumed that expectation of xi is some common mean x bar which is finite. Okay. You need a finite mean for these xi's. This basically implies that expectation of absolute xi is also finite. right. So, we will use these to prove that condition 2 as written out here holds for the sum S j, all right. So, recall that S j whose expectation we want is just I is equal to let me say n is equal to, right, n is equal to 1 to j x n, which can be written as sum over n is equal to 1 to infinity x n indicator of j greater than or equal to n, right. This we have already seen. So, the question is, can I take the expectation inside this infinite summation, and one sufficient condition is 2, which is to look at, consider this sum, consider n is equal to 1 to infinity expectation of absolute x n indicator j greater than or equal to n, all right. So, I am looking at this is my expectation of absolute y I, if you like, right. Of course, the absolute value of an indicator is just the indicator itself. So, this is just sum over n equals 1 to infinity expectation of absolute x n indicator j greater than or equal to n, right. Sorry, indicator expectation of this whole thing, and by the stopping rule property I already know that absolute x n is independent of indicator j greater than or equal to n. In fact, we proved earlier that x n is independent of j greater than or equal to n. By the same argument you can prove that absolute x n is independent of indicator j greater than or equal to n. So, this is equal to sum over n equals 1 to infinity. So, you can the expectation of this will become expectation of x n absolute x n times expectation of the indicator, which is just the probability that j greater than or equal to n. Okay. So, now this absolute expectation of absolute x n is assumed to be finite, right. This is some finite, I am going to assume that this is some finite common number, right. Let us say this is expectation of absolute x, which is some finite thing, right. So, this becomes sum over probability that j greater than or equal to n, n is equal to 1 to infinity times this expectation of x absolute x comes out, right, and this is nothing but expectation of j, because the summation is just expectation of j times expectation of absolute x. Now, we have assumed that both expectation of absolute x and expectation of j are finite. So, that this is this product is finite. Okay. So, this implies that 2 is satisfied, the condition 2, which I said is if you ensure this condition 2, then you can push the summation the expectation into the infinite sum, all right. So, since we have proved that for S j, you can push the summation in as we did in star, right, that is justified. Okay. So, that basically completes the justification, and therefore, the proof of Wald's equality is complete. Now, I want to make a few remarks See, we have assumed the statement of Wald's equality, we have assumed the xi's to be IID random variables, right, and j to be a stopping rule for these random variables. But nowhere in this proof is the independence actually used, right. So, xi's could be dependent, okay, that is the first thing to note, right. So, the proof and the result continue to hold as even for dependent random variables. Further, we have also assumed identically distributed random variables, which is again not needed, all right. What we need is a common mean x bar which is finite. So, xi's could even have different distributions, but as long as expected x and expected absolute x for each of these xi's have a common expected value of x and expected value of absolute x, both with finite values, then this continues to hold, all right. So, maybe I should say so. The result continues to hold even for dependent xi's. Further, xi's could have different distributions. The result holds as long as expected xi is some x bar, is a common value x bar which is finite for all I, and expected absolute xi is some, let us call this eta, which is something finite. So, nowhere have we used independence, and even identically distributed is not needed. Okay. And if you look at this proof even more closely, the key step was this, that bit, right, that equality, where we use the stopping rule property, where we showed that the event j greater than or equal to n is independent of x n due to the stopping rule property. Actually, we have just used the uncorrelatedness of x n with indicator j greater than or equal to n, right. Of course, uncorrelatedness follows from independence, which is follows from stopping rule property, but really what you need is uncorrelatedness for each n between x n and indicator j greater than or equal to n. Okay. So, that is as general as you can get. In fact, there are statements of Wald's equality even when the xi's do not have a common mean x bar. You can make a more general statement which is a little bit more messy. In fact, Wikipedia has a more general statement of Wald's equality. But we can just stop with this particular version of Wald's equality with just the understanding that although we have stated it for IID random variables, you do not need independence, you do not even need identical distribution, but you do need expected j to be finite and expected xi should be some common value x bar which is finite, all right. That is all that is needed. So, this is that concludes the proof of Wald's equality.